Let's talk now about a type of molecular interaction called noncovalent or electrostatic interactions. There's so very many different kinds of electrostatic interactions, and they're really so complex and so diverse. But let's begin with one that I think you will find very familiar because you've talked a lot about this in chemistry. You've probably called it by another name. We call them charge-charge interactions, but these are ionic bonds. Ionic bonds, of course, forming between two ions, one negatively charged and one positively charged. So charge-charge interactions, as we might remember, are the type of interactions that we see in so-called electrolytes. So we know that charge-charge interactions, if they're a part of what holds together a macromolecule, a protein, then if they're on the outer and sort of surface exposed region of a protein, then they're going to be very easily broken, right? So I have a model, an old model of a protein that I made a long time ago, but this is I hope going to give you a bit of an idea for where electrostatic charge-charge interactions might be the most important within a protein. We could think about them being sometimes found superficially on a protein, maybe if the protein's interacting with something else, but if the protein is relying upon charge-charge interactions to maintain its tertiary structure, they're going to be the most important inside of the protein, say here, where they're shielded from water. Because remember that water causes charge-charge interactions to dissociate. It weasels in and pulls apart and tugs on those charges because of its polar nature. So we would find them being most important in the interior, the hydrophobic interior, where they could be shielded from the aqueous solution that the water might tug and pull them apart. So these are cation-anion interactions. They are the strongest of the non-covalent interactions, but they certainly are weakened by polar solvents. Water, of course, being the most classic of those polar solvents. So they are strong, but only as compared to other non-covalent interactions, and they certainly influence the biomolecule structure, proteins being one of the utmost and most talked about of those. So things like salt bridges, we call those charge-charge interactions in a protein, we call them salt bridges. So if there was in fact in the interior of this protein a salt bridge that was forming in this region, we would call that charge-charge interaction a salt bridge. Let's move on to the next category of electrostatic or non-covalent interactions we've talked already a lot about. These are the hydrophobic interactions. So remember mentioning that the hydrophobic collapse really is a big part of what contributes to the tertiary structure of a protein. So the overall three-dimensional look of that molecule can come in large part because of the hydrophobic interactions at the center of a protein. So we won't go more into depth about that, just remembering that the polar water molecules tend to force together the hydrophobic molecules, and that leads to those sort of collapsing sort of interactions. The last type of non-covalent interaction that I want to talk about, they're van der Waals forces, and oh my gosh, I don't know if you're anything like me, but when I was an undergraduate student, I got very used to hearing about van der Waals forces, but I'm not sure I ever entirely understood them. And maybe that's because no one ever grouped them for me and talked about the different kinds of van der Waals forces. So that's what I hope I can do here. And I'd like to begin with the strongest of the types of van der Waals interactions, the ion-dipole interaction. And you can see here that this is very much like what we talked about with electrolytes, where the ion, because of its charge, is very water-loving and is going to interact with the water. But the force that exists between an ion and a dipole is a type of van der Waals force, a type of van der Waals interaction. And we know that those are stronger than something like the next category, which would be a dipole-dipole interaction. Now, dipole-dipole interaction means that you've got one polar molecule interacting with a second polar molecule, and because of both of them having that dipole moment, they do form that interaction. And we know the most quintessential example of a dipole-dipole interaction is, of course, the hydrogen bond. And hydrogen bonds are unique because one of the members in the dipole-dipole interaction is always a hydrogen atom. So it's a hydrogen atom reacting with a small electronegative atom like oxygen or nitrogen or fluorine, and we know they are an important part of biological macromolecule structure, but they also are weakened. So if you have, say, within a protein, if you have a nitrogen interacting with a hydrogen, then it will be weakened by exposure to water. So a lot of times these have to be in areas that are shielded from water as well if they're contributing well to the overall macromolecular structure. And actually the most famous macromolecule for this kind of interaction is our molecule of life, right? DNA. I have a cheesy model of DNA as well. This is one that was built by some of my students in biochemistry, actually quite a lot of summers ago. But this is just the classic example of shielded hydrogen bonds, because the interaction that holds together the two strands of DNA are the hydrogen bonds, and they're very shielded from the outer aqueous solution so that their strength is greater. They're not pulled and tugged apart by water because they are shielded from that water. So hydrogen bonds are a favorite example of dipole-dipole interactions, and dipole-dipole interactions are stronger than the next type of interaction, which are the ion-induced dipole interactions. Now, this is kind of hard to understand, but when we picture, recall way back in your memory perhaps the electron cloud that surrounds the nucleus of any atom, and sometimes in any given moment the electron cloud may not be entirely evenly distributed. It may get a little bit off center, a little off kilter, and with that, because of that uneven distribution, there may be a moment when the attraction to the electrons can be induced by a neighboring ion. And so we can recognize an interaction between the electrons of even a nonpolar molecule because of that fluctuation, that ebb and flow in the electron cloud, that iron ion in this case may be able to interact with a nonpolar molecule like oxygen. Now, even weaker yet are the dipole-induced dipole interactions, where we see nothing quite so attractive as an ion. We just have a polar molecule where there's an uneven sharing of electrons going on, interacting with a molecule that generally tends to share evenly. But again, because of the polarity of one molecule, you can get the induction of a dipole in the nonpolar molecule. So again, the loosey-goosiness of the electron cloud. Last but not least are the ever classic London dispersion forces. And London dispersion forces are what we speak about when we talk about possible interactions between something like a hydrocarbon. Remember, hydrocarbons with their very similar carbon and hydrogen have a very similar electronegativity, so we wouldn't think of them as being able to be attracted to one another. But again, because of the possibility of the nucleus of one atom attracting the electrons of a neighboring atom, this can sometimes happen if the electron cloud density changes in one region, and momentarily it can induce an interaction called a London dispersion force. So it's awesome because in London dispersion forces, distance matters, but also don't ever let anybody tell you size also matters, right? It depends upon how large that electron cloud is around certain molecules and whether it can more easily have an induced sort of interaction in the cloud. The larger the cloud, the more loosey-goosey it can be. And so there's an effect of both distance and size. If you think about the nucleus of one atom attracting the electrons of another, at a certain optimal distance, there'll be the right it'll be the right distance for the attraction of one's nucleus to the electron of the others. But if those are pushed too close together, the nuclei start repelling one another. And if they're too far apart, they're too far apart to feel the attraction to the neighbor's electrons. So there's both an effect of distance and of size here. So these are momentary dipole inductions in neighboring atoms, and the strength depends upon atom size, and forces only exist at optimal internuclear distances, and we'll look at that just a little more here in a moment. But I want to take just a minute to maybe place this in something that you know well, and I hope many of you, like me, like to cook, and we'll be talking more about that later, I promise. So when you are about to boil pasta noodles, a lot of times we'll put salt in the water. And the reason that we put salt in the water is to raise the boiling temperature, because we're adding a strength to the interaction. So remember, within water, hydrogen bonding is what holds it together, causing the heat of vaporization to be high. But we can raise that even higher by adding in an ion, the sodium cation, to interact with sodium and chloride cations to interact with the water molecules, causing ion dipole interactions, and therefore making even stronger interactions between the water, keeping the water from vaporizing and boiling until the temperature is even hotter. So I hope this helps you connect van der Waals forces to your life.
This idea that London dispersion forces only occur at an optimal internuclear distance can be summarized using a graph. On this graph, you'll notice that the y-axis is energy. We could think of that as the strength of attractive forces. And if we mark the 0 point, which I've done with a dotted line, then attractive forces will be below that point, and those repulsive forces, where nuclei are repelling one another, will be above that point. Now, the internuclear distance is on the x-axis, so we're showing energy as a function of that internuclear distance and looking for that optimal internuclear distance at which the van der Waals forces or London dispersion forces exist. Now, we can picture two atoms where very far apart they have very little interaction with one another, and certainly the nucleus of one does not attract the electrons of the other, so we would picture the energy sitting right around 0 at that point. However, as those two atoms come closer to one another, we see the loosey-goosiness of the electron cloud, we know that there's an optimal distance at which the nucleus of one attracts the electrons of the other. And then we begin to see the attractive forces increase until we hit some optimal distance where London dispersion forces are the greatest. So right here at this minimum in the graph, we see that that is the most optimal London dispersion forces. We actually say that that occurs at the point where we define as the sum of the van der Waals radii. So this is the optimal attractive force right here. And we would define it as the sum of the van der Waals radii. The optimal attraction. And of course, as those two atoms come closer and closer together, then the forces become repulsive because the nuclei are sensing one another and are repelling one another. So as internuclear distance becomes closer and closer and closer, you begin to see that function rise up above 0, and the repulsive forces come to a maximum. So again, internuclear distance is everything when it comes to London dispersion forces, and it's only at the optimum internuclear distance that we see that those attractive forces being maximized. Awesome.